So now we will proceed to the next part of the question. C says the string is cut so that the spring extends upwards. This causes the beam to rotate and launch the block into air. The block reaches its maximum height and then falls back to the ground. Fig 2.2 shows part of the path of the block in the air shortly before it hits the horizontal ground. The block, so this diagram here, as you can see, is one that they are talking about. They say that it shows the path of the block in air shortly before it hits the ground. So it is hitting the ground here at B. Here it is not yet hit the ground, but as you can see by this arrow, it is going towards the ground. Okay, so the block is at a height of 0.090 meters above the ground when it passes point A. So when it passes point A, it has a height above the ground. The block has kinetic energy of 0.044 when it hits the ground at B. So at B now it has a kinetic energy that it has. Calculate the decrease in the gravitational potential energy of the block as it moves from A to B. So we want to find the decrease in gravitational potential energy. So how do you find the decrease in gravitational potential energy? That's the question there. Okay, so we have the height that we are given. So we write the formula every time when you're told something like that one, unless there are some complicated things. It's so simple. We just write the formula that delta GPE is equals to mg dot mgh or delta h. We have our mass that is given there from the previous part of the question. Let's go back to the previous part of the question. We will see the mass of the block. So the block actually had a weight of 0.30. So if the block had a weight of 0.30, so then it is important to know that if that is its weight, then we know that is weight. We know that weight is equals to mg, and that weight is 0.30 newtons. So mg is 0.3. So here we don't come by trying to find mass. We know that mg is already 0.3 times the height. The height is given here, it's 0.090. This is the height that it loses from A to B. When it moves from A to B, the height that it loses is 0.03. So that's the decrease in that causes the decrease in gravitational potential energy, which is an energy an object possesses due to its height above the ground. So when we multiply this one, we'll get 0.027 joules. So that is our gravitational potential energy decrease, 0.027. So there's that decrease in gravitational potential energy. Now the next part of the question says, use your answer in C1, the 0.027 that we just found, and conservation of energy to determine the speed of the block at point A. So we want to find the speed of the block when it was at this point A here. What was its speed? But we are going to use the conservation of energy. So if you're going to use conservation of energy, we need to know the energies that it had at A and the energy that it now has at B. Where is the energy coming from? Now remember, the question is clear here that we have to assume that air resistance is negligible, meaning that none of the energy in this motion was converted into heat by air resistance, by work done against the body by air resistance. So none of the energy is lost. Energy is having only two forms: gravitational potential energy and kinetic energy. So we will start off, of course, by understanding what was the energy we had at point A. At point A, let's say we had kinetic energy. Okay, maybe let me write it in terms of letters, words. Let's say kinetic energy at A, which we don't know yet, plus the gravitational potential energy, GPE, at A. Then we go further and say kinetic energy at B plus the gravitational potential energy at B. It's only logical that we have to do it this way, considering that energy is conserved. So the energy we have at A should be equal to the energy that we have at B. Okay, fine. Remember, we're looking for the speed at A, so we need to know the kinetic energy at A. So what do? I say kinetic energy at A is equals to kinetic energy at B plus, we still have gravitational potential energy at B minus, because we have taken gravitational potential energy at A to the other side. Okay, that is fine. But we have to be very careful now in our subtraction here, as I shall show you why. We have to be careful because we know that the value of gravitational potential energy GP at B is less than the value of the gravitational potential energy at A. So it's more like we are subtracting a value of this one which is less than the value of this one. If we subtract the two values, obviously a lesser value minus the bigger value will give us a negative value. So it is important that we take care of that one, because it will affect how we are going to approach this part now. We know that at the kinetic energy at B is 0.444. However, here we are going to say, since we have subtracted, because we know that the decrease in gravitational potential energy from A to B is 0.027. That's the difference between the two values. So, but if we say GPEB minus GPEA, then obviously we will get that value as a negative. That's why we will write negative 0.027 here, because of this reason. So then we subtract these two. That will give us the kinetic energy. So next now, we know that kinetic energy is half mv squared. So kinetic energy at A is now that what we were trying to find now, because we want to find the speed at A. So I think that then we can go and say, since we know that weight is equal to mg, then m is equal to weight over g. Then we come here and we say, okay, half weight, which is 0.3 over 9.81 is equals to, okay, there's the v squared also here. V squared is equals to 0.044 minus 0.027. I think that if we subtract these two, we'll get approximately 44 minus 27. I think that we'll get approximately 17. Yeah, so it's 0.017. Yeah, that's it. So then we go further with it. Then we multiply both sides. We say half, multiply both sides by the denominator here. So for now, just leave 0.3 here. V squared is equals to, I've multiplied by the denominator of the left hand side, both sides. So it should be 2 times 9.81 times 0.017. Then we divide both sides by 0.3. It becomes it becomes 2 times 9.81 times 0.017 divided by 0.3. So V squared is equal to that. But so that don't waste time, we just find the square root of both sides now. So by finding the square root of both sides, we will find that our answer for V is 1.1. So we write our 1.1 in the space given there. It's 1.1 meters per second. Next now, by reference to the force on the block, explain why the horizontal component of the velocity of the block remains constant as it moves from A to B. Now it is important also for you to know that when it is moving from A to B, the block is almost in projectile motion. But you must know some things about projectile motion. When there is no air resistance, the acceleration is only vertical. But if there's no resistance, that acceleration, which is vertical, is 9.81. Horizontally, the acceleration will be 0. So there is no horizontal acceleration. Now, you might ask, why don't you have horizontal acceleration? Because acceleration is a function of us having a resultant force. But a resultant force is equal to mass times acceleration. So if you have to have acceleration, then it must mean that we have a resultant force. But for us to have resultant force, it means that we must have forces acting on the body horizontally. Now since there is no air resistance, it means that we have no horizontal force at all, because we are not told of any. It's a projectile motion. It has been thrown. It's an object that has been thrown, so it cannot be having a forward force, neither can it having a backward force. There's not even air resistance. So the only force that we have is a vertical force, which is weight. So we only have a vertical resultant force. We don't have a horizontal resultant force. We only have a vertical resultant force. So that's why the horizontal force doesn't change. The horizontal force does not change because we have only a vertical resultant force. Only a vertical resultant force. So the horizontal force is not there. The resultant force horizontally is zero. The acceleration horizontally is zero. So if there is no acceleration, then the velocity horizontally cannot change. So let me write the answer now. By reference to the force on the block, explain why the horizontal component of velocity of the block remains constant. So we'll say there is no horizontal force acting. There's no horizontal force acting on the body. So there's no horizontal force acting on the body. So there is zero horizontal resultant force and acceleration. Okay, so that's it. That's our answer there for this question. There's no horizontal force acting on the body, so there's zero horizontal resultant force and acceleration. Okay, so that's it for that question. Then the final part of the question: the block passes through A at time t is equal to A, and then arrives at point B at time t is equal to TB. On Fig 2.3, sketch a graph to show the variation of the magnitude of the vertical component of velocity of the block. So we want to have a graph of vertical component of velocity of the block, how it varies with the time, from time when it is at A and to the time when it is at B, the vertical component of velocity. Now remember that at A it already had the velocity. At B, the velocity has increased. We have more kinetic energy. So the question is, how do we draw such a graph of the vertical component of velocity? Now you can never draw a graph of velocity against time unless you have an equation. And in this case, we have to use equations of motion. And in this case, I'll use this equation of motion specifically because of these reasons. Number one, we know that according to this graph, the acceleration vertically, if there's no air resistance, is the acceleration due to gravity, which is 9.81, which is a constant. So ultimately, if you check out everything here, since the graph is of v against time, we can say that v is, which is put on the y-axis, the vertical component of velocity. Since acceleration is a constant, then this equation can be used perfectly. Then this would be c, the y-intercept, the velocity at a time when the body is at a, then plus the acceleration, which is a constant, so that will be the gradient, since the graph is t is on the x-axis. So ultimately it's a straight line graph where the initial velocity is a y-intercept and with a positive gradient, considering that this object is falling down and we are treating the velocity going down to be positive, and also the acceleration is also positive going downwards. So this graph will be a straight line. Obviously the initial velocity is not zero, so it will be a straight line, something like that. Of course we can put values if you want to put values, but then we'd have to look for the final velocity at b. But this is not asking for us to do that one. They just said sketch the graph to show the variation. We have sketched the graph there.